Hello and welcome you all to the 22nd lecture of this NPTEL course, Electroweak Interactions in the Standard Model of Particle Physics. And in the last lecture, you know that we derived something very interesting, which was actually to use the local symmetry transformations or what we call the gauge symmetry transformation in specific U1 gauge transformation on the fermionic fields as well as on the gauge bosons to construct a Lagrangian where we could finally make the electron talk to the photon or derive the interaction terms, and that's precisely what drives or governs the quantum electrodynamics. And so we derived one of the most important Lagrangians that the mankind has ever been able to kind of come up to. So let's start from that point, and today we are going to take you through to some other interesting aspects of this very theory, and let's see what exactly we are going to do after that. Okay, but let's get started with the Lagrangian that we actually formed. So you remember that we utilize the gauge freedom of the photons so that we can say that the Maxwell's equations remain invariant under the transformation when mu goes to mu prime, which is mu plus del mu chi, where box of chi is equal to 0 is the equation of motion which chi will follow in a specific gauge condition. And on top of that, we prescribed that instead of having the ordinary partial derivative like psi bar I gamma mu del mu psi, we wanted to write it in terms of a covariant derivative d mu, where we wrote d mu equal to del mu minus I q a mu involving the gauge field now. And then we showed that the Lagrangian, which is psi bar I gamma mu d mu psi minus m psi bar psi, where del mu was replaced by this d mu, actually remains invariant under the transformation where psi goes to psi prime, which is equal to e to the power I alpha x psi. And this finally gives rise to what you call the QED Lagrangian. So let's actually write it once more, so that this is not an exaggeration, but this is very important for us to kind of write it once more. So let's write it. So the term was I psi bar gamma mu d mu psi minus m psi bar psi. So this is the mass term, and then of course we also have to add the kinetic term involving the photon, and which is embedded in this term minus 1 by 4 f mu nu. And you remember the definition of f mu nu was essentially del mu nu minus del nu mu, right? So this is my QED Lagrangian, and if you inflate this term d mu equal to del mu minus I q a mu psi, बाकी टर्म जैसा है वैसे रहने दीजिए. So this will give you the interaction term. The first term will be the known gamma mu del mu psi, and the second term will be plus q psi bar gamma mu psi a mu, right? And बाकी टर्म जैसे है वैसा है. So this is the source term like j mu a mu, where j mu is, you can define it like q into psi bar gamma mu psi. So this gives rise to the interaction with the fermionic current with the photon field, and the reason that it can interact with it is the proportionality with this q, and this q is sort of idealized or identified as the electromagnetic charge. So for, or you can also say that this is the U1 charge with which this transformation occurs. Now this automatically brings this question back, that is this current interaction that we are talking about, or is this charge that we are talking about has to do anything with the Noether current and Noether charge? Because we have already seen that when there is a symmetry, then there is a conserved current and then there is a conserved charge along with. So that's the question that we would like to ask you, and the answer is indeed yes. because we are saying that this LQED, this is essentially symmetric under this transformation, psi going to psi prime, which is e to the power I alpha x psi, and you can rewrite this alpha x parameter in terms of this explicitly this q charge into some theta x, and the whole story remains the same, but I have explicitly introduced this q charge, and what we have done, that we have replaced the partial derivative also with the covariant derivative with this q coupling with the photon or the gauge field correspondingly. So therefore you can say that this infinitesimal transformation which keeps this Lagrangian invariant is essentially del psi, which is I q psi, right? I mean, this is what the proportionality is, and this basically confers that the conserved Noether current for this symmetry is nothing but q into psi bar gamma mu psi. Now you remember that psi bar gamma mu psi was actually the conserved current associated with the generic Dirac Lagrangian in any way, and what we are doing here, that we are basically multiplying the q charge along with, and this is sometimes what is called the electric current density also. Yeah, so this is the current density weighted by the electric charge, and this is sometimes called the electric current density, and the corresponding conserved charge is basically the q. So this is basically the point, that in these interactions, whenever you have the interactions driven by these QED processes, the electromagnetic charge q will remain conserved. So that's basically what we actually obtain from this very construction. Now the next thing will be to kind of put a dictionary ahead of us, like how exactly we should compute processes within the paradigm of quantum electrodynamics, and what are the measurable quantities like the cross sections and decay widths associated with the QED processes. And for that, what we require, the standard method of doing that is to actually look for something called Feynman's diagrams, and we will construct this Feynman graphs for different processes, and for that what we will require is called the Feynman rules for the QED. But before we go into that, we will actually talk about something interesting. There is one more step which we didn't discuss so far, which is actually to talk about some internal lines or the propagators which will connect two different vertices. So now, what is a propagator? What exactly we are talking about? Suppose we are talking about a system which is described by the ground state. Let's call it omega. Some people write it 0, so whatever way that you want to write it, there is anyway, it's fine. Now what we are thinking of a thought experiment, that suppose you are having a ground state of the system, and here you are actually creating a particle at suppose point y0 y vector, which in the 4 vector notation you can simply say y. You create a particle there, and the particle propagates up to point x, where it gets destroyed or gets annihilated, okay, at the point x0 x vector, or in the 4 position notation you can say this is x. And we ask the question that if the system remains in the ground state itself, and that exactly is given by this definition of what you call the field propagator. Notationally we write it like g plus x comma y, which is basically an expectation of this omega. Within this, what we have, that you have a particle which is created at y0 y, and a particle which is annihilated at x0 x. So this is what represents the propagator or the field propagator, and the notation g is basically because this is represented by the Green's function of this equation. Now Green's function is basically the one you can study in general, that whenever you have an equation with a source term, if you change that source to a delta function, the solution of that equation corresponds to a Green's function. So the Green's function of these equations, whatever relevant equations that we have all found out so far, that is going to give us this essentially field propagators. Okay. Now this, we have just expressed it in very generic terms, but when we have to mathematically express it in more neat way, we will basically say that it will have a theta function, where theta x0 minus y0, this is there, and we will have an omega phi x phi y dagger omega expectation. Okay, so this is what we actually require. Now what exactly this corresponds to? Now if you remember, see, I'm using the notation of the scalar field, but it is not really that we have to resort to this notation of the scalar field. You can talk about the fermionic field propagator for Dirac propagator, or you can similarly do it for the vector boson fields also. But for the scalar field, say for example, I can have phi x, phi dagger y between this sandwich between these two omegas. And what does it do? So for example, if you look into phi dagger y omega, remember phi dagger y, when we wrote in terms of mode expansions, this actually has the notion of creating particles or annihilating antiparticles, right? So similarly, when you have phi x, that will actually annihilate particles and create antiparticles. So you can say phi dagger y omega is basically creating a particle at y, right? On the other hand, phi x omega will actually annihilate particle, and theta x0 minus y0 makes sure that x0 is greater than y0. That means that the particle is first created at y0 and then it propagates to x0, and at x0 this is getting annihilated. So that's what is kept by this theta x0 minus y0. And as I say that this basic notation is true for any fields. I mean, way that I am writing is actually for scalars. For fermions, how shall we write? We shall replace this phi x and phi dagger y by just psi x and psi bar y, right? So that is the case for fermions, and similarly I can have it for the vector boson represented by mu star and nu x and mu star. Okay. So this is usually the definition of the field propagator, but this has a bit of issue, because you see that when we define this field propagator by this definition, it's basically only talks about particles, right? The particle propagation, the creation of particle which gets annihilated and so on. But we actually require both the particle and antiparticle propagation, right? So we have to somehow encapsulate both of this, and so for that, what Feynman did, Feynman proposed to use instead gxy, instead of this notation g plus xy, we use gxy, where we use this time ordered product of phi x and phi dagger y. What does it mean? It basically means that it has basically two terms. The first term is theta x0 greater than y0, which means x0 is greater than y0. That means y0 happened first and then x0, and then the term within this expectation will be omega expectation of phi x, phi dagger y omega, right? So this is what we have. So it is very clear that this is the same term that we wrote before. So this is precisely the g plus xy. But this also have the other term, because time ordered means, I mean, you can have both the contribution coming from, when x0 is greater than y0 and y0 is greater than x0. So the first term actually is the case when x0 is greater than y0. But what happens that when we have other way around, like y0 greater than x0, then I have to basically have a theta of y0 minus x0 term, and then I will change the order in which I was writing phi x and phi dagger y, and I will write phi x omega on this side and phi dagger y omega on this other side. And what does it mean? Once again, you see phi x omega, this means that it's now the creation of antiparticle and annihilation of particle, but it's more important to talk in terms of antiparticle creation. So this basically creates an antiparticle which gets annihilated at y, because x0 happens first and y0 next, because here y0 is greater than x0. So then we have the annihilation of that antiparticle at y0 given by omega phi dagger y. So basically you encapsulate both the particle creation and annihilation and antiparticle creation and annihilation by this Feynman propagator diagram. Now the question is, this part we understand, so this is something which is required in order to compute any processes that we actually see. But the question then comes that how to actually calculate this propagator, how to calculate this Green's function of the propagator. Now I am going to briefly give you a sketch of how to do that, and that is going to also give us something interesting regarding the QED Lagrangian, which I will be talking at the end of this lecture. But in general, what you try to do, that you try to rewrite your Lagrangian in terms of the fields in this particular way. So you write that Lagrangian like phi bar O phi plus some total derivatives term. Now, if this phi, once again, this phi is a generic notation and it can represent any field, represents any field. Okay. For scalar field, this capital phi is phi, and this phi bar will be essentially phi dagger, right. So, the scalar field, similarly for Dirac field, we have to rewrite the Lagrangian in this way, and for the Dirac field, which is usually our notation is psi, and then this phi bar will be then psi bar, which is psi dagger gamma 0, which we already the conjugate Dirac field, which we already have introduced. Now, what is this O? Of course, because the Lagrangian will involve primarily the kinetic term and the mass term and the interactions as the way that we have seen in the QED, right. So, this O is primarily a differential operator. This involves derivatives, right. So, this is in general true. Now, let us take an example and see how this works. So, for example, let us take the example of the scalar field theory that we actually did, which we also call the Klein-Gordon Lagrangian, because it gives rise to the Klein-Gordon's equation of motion, box plus m square phi is equal to 0, and that describes a quantum field theory for the scalar particles, right. So, let us try to write the Klein-Gordon Lagrangian, and you all know the kinetic term is del mu phi dagger del mu phi minus m square phi dagger phi, correct. Now, what you can do, that you can actually write this term in this particular way, that you can have a term like del mu acting on phi dagger del mu phi. Now, when you have del mu acting on phi dagger del mu phi, you will have two terms, right. One, when del mu will act on this phi dagger, and then this del mu will act on del mu phi, that will be the box phi. So, this will give rise to two terms. One term is the one which is right above, which is actually the kinetic term for the scalar fields, del mu phi dagger del mu phi, and the other term phi dagger box phi is not actually there in the Lagrangian. So, what we have to do, that we have to subtract this term minus phi dagger box phi minus m square phi dagger phi, right. So, this is how we can write. Now, this exactly resembles to the Lagrangian that I wrote before. So, you have this first term is essentially the total derivative term, right, which we do not worry too much. So, this first term is the total derivative term, and the second term is essentially phi dagger O phi. And so, therefore, what is your O? O is simply, or if you write it plus, so the O will be nothing but minus box minus m square. Now, what we actually need to do, that we essentially have to inverse this operator O to actually get the Green's function or the propagator. Now, in order to do that, and usually what we do, that we actually do it in the momentum space, and if we have to do this exercise actually is a detailed exercise, and you can try using your quantum field theory books, that what you have to first do is to replace this del mu by minus I p mu, because you know that p mu operator is nothing but minus I del mu. This is something that we all know, right. So, therefore, replace this del mu by minus I mu. So, therefore, the box operator becomes p mu, which is p square. So, now if you invert this operator, what exactly the form that we get? This is something obvious. We usually write it in terms of I del f p, and this will give you I by p square minus m square plus I epsilon. So, in a sense, you can also say that this momentum space propagator that we actually derived, or rather indicated how exactly it looks like in the momentum space for the scalar operator or the scalar fields, this form of the propagator is nothing but the Fourier transformation of the xy propagator that we just talked about, gxy, which is usually written as delta xy for the scalar fields. Okay? So, this is nothing but this transformation which you know that delta xy can be related to delta p by integral of d4 p by 2 pi whole to the power 4 e to the power I p x minus y delta f. Now this notation, this f which is sitting downstairs here, represents basically the Feynman propagator, and which includes both these possibilities that we talked about. Okay. And then there is one interesting part that you see here sitting here, is that there is a part which is called I epsilon, a small number which is actually sitting here, this epsilon. This essentially comes from the fact that basically we have to take the Fourier transformation of this theta x0 minus y0 also, and it turns out that when you take this in the complex plane, then this theta x0 minus y0 can be written in terms of I minus infinity to plus infinity dz by 2 pi e to the power minus iz x0 minus y0 by z plus ie. So this is the reason that we have this plus I epsilon, which is actually sitting in the denominator. This also takes care of the fact that when p square equal to m square, which is what you call the on mass shell, I mean when the particles are produced on mass shell, then the 4 momentum square should be mass square. This is something that we all know. And then this propagator basically diverges, right? This plus I epsilon that you actually have in the propagator, that essentially takes care of the fact that it doesn't actually blow up, right? So that is also another reason. Okay, so this is the form of the scalar propagator. Now let's talk about how exactly we should find out the propagator when you have the fermion propagation. Now this operator, once again you have the Dirac Lagrangian, and your job is to rewrite the Dirac Lagrangian in this particular form, like I did, like phi bar O phi plus the total derivative term. And if you want to do that, it turns out that the operator concerning the Dirac fermions will be simply I gamma mu del mu minus m. So basically now once again what you have to do, that you have to invert this operator to find the propagator, and so therefore you can simply say this is I by p slash minus m, right? Or p slash, what is p slash? P slash essentially is gamma mu p mu, right? So this is I by p slash minus m, and what you can do, that you can actually multiply p slash plus m up and down, so that you have in the denominator p square minus m square, and in the numerator you have a p slash plus m, and once again the plus I epsilon has to be added here in the denominator, and this gives you a form of a fermionic propagator. Okay, so for Dirac fermion, the propagator actually looks like this. All right. Now the next challenge is to find the propagator for the gauge bosons or the photons, so to say. Now photon propagator, once again we have to find out something like this, omega, this time ordering mu x nu y omega, and this will be a Fourier transform of pi mu nu p, say for example, which will be I integral of d4p e to the power I p x minus y pi mu nu p, right? This is something that we need to find out. What was the Lagrangian for the photon fields? The Lagrangian usually involves the kinetic piece, which is minus 1 by 4 f mu nu f mu nu. Now what QED has told you, that QED has told you that there is an interaction with the photon, and there is a term like minus j mu a mu, correct? Where we actually wrote that this j mu is essentially something like q into, or rather here if I am writing minus, then this is minus q psi bar gamma mu psi, correct? Now if you write the equation of motion, so this exercise is something that we have done in our earlier classes, so you can find the Euler-Lagrange's equation of motion, and it is very easy to show that this will turn out to be del mu f mu nu j nu. So this is my equation of motion if I use the Euler-Lagrange's equation. Now just because f mu nu is defined as del mu a nu minus del nu a mu, so I can say that on the left hand side I have del mu a nu minus del nu a mu, that is actually equal to j nu. And if I want to write it in the momentum space, how do I do? Once again use this trick, that I am going to replace the del mu by minus I p mu, minus I p mu. So this equation in the momentum space turns out to be minus p square g mu nu P mu, P nu, A mu is equal to J nu. So, once again it is very easy to see that each of this, so this del mu is replaced by minus I p mu, this del nu is represented by minus I p nu and so on. And what we have done, that we have actually used the proper contraction, and this one actually will have p square g mu nu, because I am actually bringing this nu to be mu and making it down. So, a little bit of algebra. This is not very difficult to do. So, this is how exactly we have this equation. Now, what we want to do, that we want to write this A mu equal to pi mu alpha j alpha, right, and this pi mu alpha will actually give us the propagator, right. So, this is what we want to do, that A mu equal to pi mu alpha j alpha, this is how we want to write. So, let us do that. So, let us replace this A mu here by pi mu alpha j alpha, and here on the other side just I want to conserve the notation j alpha. So, this will be j nu can be written as g nu alpha j alpha, right. So, therefore, if I ignore the j alpha from both sides, what we have, I have an equation which is like minus p square g mu nu plus p mu p nu pi mu alpha is equal to g nu alpha. So, you can imagine that this is basically the Green's functions of this equation. In turn, this is the propagator for the electromagnetic field. But now there is a trouble. The trouble is that in order to take the inverse, what we have to do, that we have to find the determinant of this prefactor, like p square minus p square g mu nu plus p mu p nu, and it turns out that this determinant is identically 0. And this is 0, this essentially follows from the fact that this minus p square g mu nu plus p mu p nu has 0 eigenvalue with p mu as its eigenvector. Now, this is something that you can easily check. So, we have a trouble in deriving the propagator for the vector boson field or the photon field, just because we need to invert this minus p square g mu nu plus p mu p nu, but I cannot do that just because the determinant is 0. So, the kinetic term cannot be inverted to find the propagator, as we have done for the other cases, for the fermion and the scalar cases. Now, what shall we do? How to resolve this issue? There is one way of doing it, which is to add a term explicitly by hand, and that is what is called the gauge fixing term. Okay? So, the way that you do that, you basically add to this Lagrangian a term explicitly, which is like minus 1 by 2 zeta del mu a mu whole square term. Now, this term was not there before. I am just adding it by hand, and I can, so where this xi or zeta, whatever that you want to say, this is actually a parameter. Apparently, the value of this parameter is not fixed. One can actually take any value of this psi, and this should not affect my outcome of this theory, right? That is the idea. However, one thing that we observe is that if we want to keep this xi or zeta equal to 0, then this requires del mu a mu equal to 0, correct? Because otherwise this term will not be defined. So, xi equal to 0 necessitates del mu a mu equal to 0. Now, do you recall that del mu a mu equal to 0 is actually a specific gauge condition, and that is precisely what we called Lorentz gauge condition, right? So, you can say that fixing xi will actually give me a gauge fixing condition, and that will give me Lorentz gauge. For example, xi equal to 0 has to have del mu a mu equal to 0, which is Lorentz gauge. Okay. Now, once again, this vision must be complete, that what did we do? That we said that okay, we cannot invert the kinetic term in order to find the propagator for the gauge field or for the vector field. So basically what we did, that we added a gauge fixing term here in the Lagrangian, and then we can try inverting them. And the point is that the kinetic term cannot be inverted using zeta equal to 0, but what we can do, that we can invert this and then take zeta equal to 0, and that is completely allowed, and then we basically find the rules of the propagator in the specific gauge condition, which is the Lorentz gauge condition. Now it turns out that if you find the equation of motion using Euler-Lagrange's equation of motion for this particular Lagrangian, then this equation of motion, so you remember the first one, it was like minus p square g mu nu p nu a mu equal to j nu. Now you can imagine that this will be very similar, but there will be a dependence on this parameter zeta that we have introduced, and it turns out that this equation of motion will be minus p square g mu nu plus 1 minus 1 by xi p nu a mu is equal to j nu. So this is my equation of motion. Now this is a non-trivial exercise. So this part you understand, and now this part of the matrix, this is an invertible one. You can indeed invert this one, and this process is not a very trivial one. It's a exercise that you should try. Okay. So if you invert this one, then basically you achieve the propagator, right? And that propagator will basically have the form like I pi mu nu p will be minus I by p square plus I epsilon g mu nu minus 1 minus zeta p nu by p square. So this is the form of the propagator. Okay. So this is the form of the propagator, but remember that this form of the propagator explicitly has this xi or zeta in it, in this one. Okay. And this is what is called the photon propagator in R xi gauge, because I have not chosen any specific xi, and this depends on the gauge choice. But interestingly and importantly, you will see that when we calculate the processes, I mean the outcome of different scattering processes, it doesn't really depend on the photon propagator parameterization that we are doing, and this is an interesting consequence of the gauge invariance itself. But for the time being, what we do, that we fix a specific gauge which is called the Feynman T-Hooft gauge, which is commonly utilized, and we will be utilizing most of this particular gauge in our calculations. And in this one, how exactly this propagator looks like? The propagator will look like minus I. So the zeta equal to 1 basically make this second term vanish, right? So therefore this will be minus I g mu nu p square plus I epsilon. So this is the form of the propagator of the photon in Feynman T-Hooft gauge. I mean this is the one that we will use, but as I say that there is no problem in using the other gauge, for example Lorentz gauge, where zeta equal to 0, that is actually often used, and so on and so forth. So this is actually an interesting point, and I think we are going to end the lecture here with this note, that for any quantum processes there are propagators which actually are there, which basically tells you that how this interaction is carried by from one point to other, and that is basically formally defined as the expectation of omega T of the field and the field dagger on the vacuum, and then you can calculate the propagator for any cases, for the scalar field cases, for the Dirac field cases, and also for the vector field cases for the photon. And with that we actually find out that the propagator essentially associated with the fermions is something like I of p slash plus m by p square minus m square plus I epsilon, and for the photon it turns out to be minus I g mu nu by p square plus I epsilon in a specific gauge where zeta or xi is equal to 1. But remember once again, the choice of the gauge is not going to affect our results or calculations when we do it actually for different QED processes. Okay, so with that, I'm going to stop here and I'm going to see you in the next lecture. Thank you.